Hello and welcome to the webinar Cathodoluminescence Explained, Episode 1, an Introduction. David Stowe is the product manager at Gatan responsible for cathodoluminescent products, and he is our presenter today. He has almost 20 years of experience in CL, beginning with his use of CL spectrometers to characterize the light emission from crystal defects in silicon to gain his doctorate from the University of Oxford. He then joined Gatan as an application scientist and more recently as a product manager. Whilst at Gatan, he has worked collaboratively with researchers in a wide range of applications, developing new analysis methods and CL instrumentation for scanning and transmission electron microscopes. If you have any questions during this webinar, please submit all of them through the questions pane on the webinar bar on the right hand of your screen. Any issues that come through in that pane regarding connectivity and webinar viewing, I will address immediately. All questions will be answered after the presentation. If we run out of time, all questions will be answered within the next week by David directly via email. Please submit any and all questions, and I think we're ready to present. David, it's yours.
Thank you, Parker. Hi, good morning, good afternoon, or good evening, everyone, depending on where you are in the world. Thank you for joining us. So today, the webinar topic is Cathodoluminescence Explained, and this is the first episode, an introduction. And it's going to be, I hope, a series of largely educational webinars that we're planning to host over the next 12 to 18 months. And we plan to hold these every sort of 6 to 8 weeks. And have some of them may be shorter than others. This one today is probably about 45 minutes to an hour. But we'll host these and there'll be a range of topics, and there'll be a resource really for people who are new to cathodoluminescence, discovering what it may be able to do for them, or looking to develop their understanding further. And future webinars will have a range of different focuses. Some will be very much application specific, so very focused on terms of what solutions and answers cathodoluminescence or CL can give you. Others may be more focused on instrumentation or data analysis with some scientific background, or it could be a practical hints and tips session. So there'll be a wide variety of topics that we'll cover. Something that I would really like is for people who are listening in the audience to provide us feedback, and so that we can focus these webinars so that they are more appropriate to your needs. So I'll give you more details on this at the end of the presentation, but we would very much welcome your feedback to develop this series according to your interests. So this webinar is going to be available online to use at a future time, or you can share it with colleagues. And additional resources such as websites are being developed in order to support this series. So there's a whole lot of educational activity we are doing at the moment in order to try and spread the word about what cathodoluminescence can do for researchers in various different application fields. So today's presentation, Cathodoluminescence Explained, Episode 1, an Introduction, we're really going to start at the beginning. So we're going to start explaining what cathodoluminescence is, why is it useful, and importantly, how is it being used to gain important insight into different types of materials and devices? Although I'll do a little bit of introducing the analysis modes of cathodoluminescence microscopy, I'm not going to spend too much time focused on the practicalities of it today. My emphasis today will be on sharing with you what sort of understanding the technique can deliver for common applications. So we're going to be looking at a few different use cases from the geosciences, optoelectronic materials, compound semiconductors, and nanophotonics. Okay, so let's begin. So luminescence. Luminescence is the emission of photons from a solid when it's excited by an energy source. And there's a variety of different energy sources that could be. We actually live with luminescence around us pretty much every day at the moment, particularly in the form of light-emitting diodes and solid-state lighting. Electroluminescence is around us everywhere. But there's also other types of luminescence techniques, including photoluminescence, and that's used in biological markers for biological and cell research. And what we're going to talk about almost exclusively today is cathodoluminescence. And cathodoluminescence is simply the luminescence emitted from a solid when the exciting energy source is electrons. Most of you who are at least my age and older will have some understanding of cathodoluminescence, because sat in the corner of your parents' house when you were younger was a cathode ray tube based television, and that was cathodoluminescence in action. You've all seen cathodoluminescence. So in those devices, in those televisions, an electron gun fired electrons through a vacuum tube to a phosphor screen. That phosphor screen took the energy from the electrons, converted it into light for our eyes to see. So that's how we saw the pictures in those early televisions using cathodoluminescence. So cathodoluminescence is visible wavelengths, but it also extends outside of the visible wavelengths into the ultraviolet and into the near and mid wavelength infrared. So this section of the electromagnetic spectrum, somewhere in the middle, covering from the ultraviolet, about 200 nanometers, through to the mid wavelength IR, would be termed luminescence or cathodoluminescence if we're exciting with electrons. So cathodoluminescence has actually been known about for a very long time. It was actually discovered by a researcher, William Crookes, in the late 19th century, so almost 140 years ago, and he was working on steering electron beams within a vacuum tube. And within that scientific article, extracts are published at the top of this slide, almost as an aside, he reported that many natural minerals and gems shine with great splendor when they're hit by the electron beam in his apparatus. And particularly important, he noted that diamonds from other localities shine with different colors, such as bright blue, pale blue, apricot, red, yellowish green, orange, and bright green. So all colors of the visible spectrum, but all the same material. And this was a puzzle at the time. It wasn't really understood. But thankfully, with research, we've been able to understand those things now. So now we know that what he observed in those colors was actually associated with trace element chemistry. And this is why CL is used extensively in microanalysis of geological materials, because it is a very sensitive technique to revealing trace element chemistry. So today we use primarily electron microscopes in order to be able to perform cathodoluminescence microscopy. So this is a schematic of a scanning electron microscope, but it could equally be a transmission electron microscope. We have an electron source that fires electrons at our sample, and those electrons interact with our sample, and our sample transforms that initial electron energy into light. Now, electron microscopes are really useful, because not only do they give us a source of excitation for getting the light out of our specimen, but the electron beam can be readily controlled. And what I mean by that is that we're able to focus it down to potentially sub-nanometer probe sizes. We can position it on a sample with very high precision, and we can rapidly and controllably move that around a specimen to analyze specific regions of the sample, or scan it to form a map. All you have to do is to detect cathodoluminescence is attach a detector to the side of the microscope. And here, this is an optical spectrometer attached to the chamber of an electron microscope. And detectors typically use a reflective objective, so a mirror, that collects the light that's been emitted from your specimen, taking it outside of the vacuum system into some analysis hardware. We'll go in future webinars into a little more detail about what goes on inside the detectors, so I'm not going to focus on that today, other than to say that you need some sort of light-sensitive detector and analyzing equipment to do this sort of cathodoluminescence analysis. Now, while we have our specimen in the electron microscope, it's not just light coming off of your specimen that we can collect and analyze. You also have many other signals. And these other signals tells us information about the size, shape, surface features, composition, crystallography, microstructure, all sorts of things about our specimen. This is one of the important parts of cathodoluminescence microscopies, is that it allows us to carry the optical information we get from the cathodoluminescence signal with the chemical and structural properties of the specimen. And that's right from the macro scale, so many, many millimeters in size, right down to the nanoscale, So cathodoluminescence is a meeting between electron microscopy and all of the analytical techniques you have in electron microscopy and luminescence spectroscopy. So luminescence spectroscopy allows us to understand the optical and electronic properties of materials. But importantly, this marriage of the two techniques in the same experimental apparatus has very significant advantages. So compared to other luminescence techniques, cathodoluminescence has the ability to deliver very high spatial resolution. And that's because the spatial resolution is limited by the interaction of your specimen or the electrons with your specimen, rather than the diffraction limit of the way in which you manipulate the light in the excitation process. It also allows you to easily excite a very wide range of materials, including insulators, semiconductors, and metals. So we can study things like minerals, gems, ceramics, semiconductors, and metals. All provide light and allow us to understand the specimen in some way. To give you a sense of scale in terms of how much improved the spatial resolution is, I put together this slide as a way of comparing between various different common luminescence techniques. Okay, so it doesn't really matter what this specimen is at this time. We'll come back to it later in the presentation. But it's a collection of nanoparticles. Each individual nanoparticle is about 100 nanometers in size, and they're kind of agglomerated together as they've been deposited on the specimen. Now, perhaps the most common form of scientific analysis using luminescence spectroscopy is photoluminescence. So photoluminescence uses a laser to excite the specimen and then measures the wavelengths of light that are emitted at a different wavelength. But with light, when you shine the laser onto the specimen, you're unable to really focus it down to a very tight spot. And so with photoluminescence, you actually, in this instance, would excite pretty much all of the particles that you see in the screen. So first of all, you would have no idea that the particles were actually on that bit of the sample that you're looking at. You don't know how many there are because you can't see them. And secondly, you're getting an average global property. And so when you then take the sample away to characterize the size or shape or structure or composition and compare it to your luminescence results, there's a potential mismatch in the information that you're gathering. Now, it is possible to do slightly better using some clever optical effects and perform a technique called microphotoluminescence, where you can focus the beam down to something of the order of a few hundred nanometers. But even in that case, you're exciting multiple particles. And so the information that you see is, again, averaged over the whole particle or between lots of different particles. So these spots are indicative of the type of spatial resolution that you can achieve. Now, added in green on the left-hand side of the page, just here, is the excitation spot in a scanning electron microscope using CL. You see that it's much smaller than a particle, probably on the order of a few tens of nanometers, maybe 10, maybe 20 nanometers in total is spatial resolution. And for clarity, I've shown that on an individual nanoparticle there. You can see that the excitation spot for CL is much smaller than the particle and would allow us to get spatial information within the particle. If you go to a different type of electron microscope, a transmission electron microscope, the potential spatial resolution is again improved, and people have demonstrated something of the order of 1 nanometer of spatial resolution in that type of instrumentation. So really, there is a fantastic advantage in being able to get optical information at nanometer length scales using cathodoluminescence. And that's one of the reasons that it's so attractive. So here we have single points that we're exciting the specimen at, but in an electron microscope, a scanning electron microscope, or a scanning transmission electron microscope, we can actually steer the beam around the sample and raster it to create maps. So we focus the electron beam on the sample, it emits light, and we analyze it in some way. We measure its intensity or its wavelength distribution, so a wavelength spectrum or color. We can also analyze properties such as the polarization state of the light that's emitted, or the emission direction, so the angle at which the photon, or the direction in which the photon exits the surface of the material. And we can do that from pixel to pixel across an array of pixels, forming a map. So on the next slide, I'll give you a couple of examples. So this, first of all, is a secondary electron image of a geological sample. It's a collection of polished grains mounted in an epoxy mount of some heavy mineral separates. And these grains are a variety of materials, and you can see there is some small contrast between different particles. For example, this one here and its neighbor have slightly different intensities, and that intensity difference is because they're made of different materials. But internally within all of these grains, there's very little to see. If we look at this now using the information we get from cathodoluminescence, all of a sudden you see a lot more detail within the crystal structure. That's because here we're getting information not only about the type of mineral that it is, but also about the trace elements within the crystal and how they're distributed. And this distribution of trace elements tells us something about how this mineral was formed and what it's been exposed to over its lifetime. So this is purely an intensity map. So we simply measure at each pixel in this image an intensity and plot it on a intensity scale, with white being strong and black being dark. But we can also analyze potentially, with the right instrumentation, the wavelength of the emission, so the wavelength spectrum, and or the color. And if I do that, then you can see that there is a lot more information available if we analyze more than just the intensity. Now, this color variation also tells us that we have different types of trace elements that have been incorporated within the crystals. Okay, so wavelength information and spatial information tells us a lot about the distribution of these different types of trace elements within the minerals. If we look at one of these in a little more detail, you can see some of that fine zonation within these individual grains, which are the result of how the mineral was formed many hundreds of millions of years ago. So that's collecting intensity and wavelength information as a function of space, but we could also do this with polarization information or the direction, the emission pattern of information. And those two types of analysis modes have only very recently been made available to researchers using the latest generation of CL equipment. I'm going to talk a little bit later in the presentation about how those are used, but I'm not going to focus too much in the way that that's done at the moment. But I will share with you a couple of examples of where these polarization and the direction or the emission pattern are important parameters to know about some types of materials. So this revealing the distribution of trace elements within minerals is actually very important for understanding geological histories. So it can tell us how crystals initially formed, the types of temperature and pressure that they formed under, and whether they've been exposed to different events in their history which have changed their structure. So here we're looking on the left-hand side, a secondary electron image of 3 zircon grains, and on the right-hand side, or in the center of the screen, but on the right-hand side of these two images, a CL intensity map. And the bright parts in this mineral correspond to regions where you have a high concentration of uranium. And this is actually an interesting trace element that's preferentially incorporated into this crystal because it acts almost like a geological clock. So uranium undergoes radioactive decay to lead. And in these minerals, uranium cathodoluminesces strongly and appears bright, whereas lead decays, lead does not emit light, and so those regions which are rich in lead appear dark. And what this allows you to do using isotope analysis and CL to guide you is to date these minerals when they were formed and when they were formed. So if we look at this crystal on the right-hand side of the screen, you can see that the core here is dark in the CL image, and it has a rim around the outside, which is very much brighter. So here, this particular grain first crystallized based on the lead isotope analysis, something like 1 billion years ago. So these dates from the central region of the grain correspond to a mineral formed about 1 billion years ago, whereas this bright region around the outside corresponds to this cluster of data points here. So this is mineral formed about 400 million years ago. So at some point in this crystal's life, it was initially formed about 1 billion years ago, and then went through some event which melted the outside of it, it recrystallized, and the outside of it is much younger. Now, being able to see this core rim effect is really important for when you perform geochronology type analysis using laser ablation techniques. You need to be able to ensure that you're within entirely one of these bright or dim regions. Otherwise, you're going to get information which is incorrect, an average of the two, which doesn't really correspond to either. So accurate dating of these geological minerals requires pre-characterization using CL mapping in this way. Now, CL mapping can also be used to quantitatively perform trace element analysis in some minerals and gems. And an example of this here is titanium in a form of quartz. We have a CL map with 3 locations shown on it, 1, 2, and 3. And in another technique, laser ablation, again, researchers have gone away and measured the titanium concentration. You can see that points 2 and 3 have similar titanium concentrations, and point 1, which is brighter in the CL image, has a much stronger titanium concentration. However, when we look at the CL spectrum, you can see that the emission spectrum at these points is not the same. What you actually observe is that the emission that occurs at an energy of 2.7 eV, so wavelength and energy are interchangeable, is directly associated with the titanium concentration, whereas the other peaks are not. So here, by having wavelength information, we're able to directly associate one of the peaks with the titanium concentration and form a calibration curve that allows us to quantitatively determine titanium concentration in these minerals. And performing this sort of analysis in CL is much quicker and has higher spatial resolution than other techniques available. And so once you have this ability to perform quantitative titanium analysis to determine the concentration of titanium in these quartz minerals, you can actually then work back and calculate the temperature of formation of the mineral itself. Now, these minerals are very important in oil and gas extraction. They are reservoir materials which hold a lot of the world's supply of oil and gas, and understanding the processes in which these form and how they form are important to the way, are important for researchers and oil and gas companies to optimize the way in which they extract oil and gas from different rock beds. So far we've looked almost exclusively at minerals, insulators, or ceramics, where the luminescence is determined by trace element chemistry. I'm going to move on to a different class of materials now, and that's semiconductors. And semiconductors form a very important or a very wide range of the applications that CL is used for. And in semiconductor materials, luminescence characterization is absolutely critical for revealing the electronic structure of a material or a device. And the electronic structure really governs the device performance for a whole wide range of technologically important devices. So transistors, lasers, light-emitting diodes, solar cells, and the list goes on and on and on. So being able to characterize the electronic structure of semiconductors is of vital importance. Not only being able to characterize it, but really we want to try and understand and control these properties to create more efficient devices or devices with novel properties. And particularly with the advent of nanotechnology, luminescence characterization that has the ability to characterize this luminescence information with nanoscale spatial resolution is becoming important increasingly. And cathodoluminescence is just that sort of technique. So apologies to those of you who are non-physicists in the audience, but it's not critical that you understand what these diagrams are, but for those who are directly involved in semiconductor research, these will make a lot of sense and will help in terms of understanding the type of information that CL can provide. So this is an electronic structure, a band diagram of a semiconductor, and it simply tells you where electrons are, what energy state electrons are within the material, whether they're tightly bound to the atom or whether they're free to wander around the crystal. So if they're free to wander around the crystal, then they're in the conduction band. And when we shine an electron beam on a sample, we actually generate free carriers within semiconductors. So the things that carry current, the electron beam stimulates those, and we create something called electrons and holes. And these electrons and holes have excess energy and they're free to move about, but eventually they recombine. And when they recombine, they emit a photon. And the wavelength of the photon is directly related to the energy transition that took place. So we can use optical spectroscopy to understand the electronic processes that are going on within the material. And an example of that is using cathodoluminescence to measure the band gap in a cadmium telluride alloy. So here we have a semiconductor alloy, and in this central region here, this is a cross-section of the device. This is the cadmium telluride layer, and this is a light absorber in solar cells. It's a polycrystalline material, and its band gap can change. But cathodoluminescence microscopy allows you to analyze the band gap of these materials. So we place the electron beam on the sample, it emits photons, we take those photons into some sort of optical spectrometer, some cathodoluminescence detector, and we record a spectrum. And from that spectrum, we can determine what the band gap of this material is. So this is analysis at a single point, but if we repeat this analysis over a series of points, then we can map the band gap in these materials. And that's actually really important. So cadmium telluride wasn't chosen out of thin air. It's actually a technologically important material. It's a solar cell material. It's the absorber layer in this cadmium sulphide, cadmium telluride solar cell. These are flexible solar cells that can be printed, very low cost and relatively high efficiency. However, during the manufacturing of these devices, the sulfur becomes mobile, and it diffuses from the cadmium sulphide into the cadmium telluride, forming an alloy. Now, whenever you alloy semiconductor materials, you change their electronic properties. You change the band gap of the material. And when you change the band gap of the material, you change the device performance. And so it's critical for researchers to be able to measure and control the band gap of this material through the thickness of the film and also laterally as well. So understanding where sulfur goes and how much of it goes is critical to developing more efficient solar cells. And so we can use CL mapping to reveal the spatial variation in the band gap energy. And furthermore, we can correlate that with the microstructure of the material. So reveal with grain boundaries, extended defects, and those sorts of things. So here's that micrograph that I showed you on an earlier slide, here we have our cadmium telluride layer. It's polycrystalline. You can see these lines here correspond to grain boundaries within the material, and there are twin boundaries in it. And then at this blue line, there is a very thin layer of cadmium sulphide, and the sulfur from that diffuses into the cadmium telluride during device processing. So we can use CL to map the bandgap. So at each of these pixels within this data set, we've captured a CL spectrum and determined the bandgap of the material. You can see that map here on the right-hand side. You can see that we have a change in the bandgap as we go through the thickness of the material, but also at the point where we have a grain boundary, we also see a significant change in the bandgap compared to its neighbors. So the crystal structure and the grain boundaries play a very important role in controlling the electronic properties in this material. And of course, once you know the bandgap, you can calculate back to the sulfur content. So you can get back to the alloy concentration as well. So that's a very simple case of semiconductors. Many semiconductors contain crystal defects, and crystal defects play a very important role in, and mostly a bad role in terms of device performance. So crystal defects, when they're electrically active, put an energy state into this energy gap. And that offers an alternative mechanism for the recombination of the electrons and the holes to happen. And when these electrons and holes, when they recombine via these deep levels, that process does not release a photon. So we don't get light out of these materials near a defect. And so recombination is a competitive event, and if electrons and holes are recombining via the deep level, then the probability of getting a photon out of the sample close to a defect is dramatically reduced. So here, let's take an example of a perfect semiconductor film. And if we shine our electron beam on it, we generate electron hole pairs, they recombine and they emit photons. However, if we now move to a region of the sample where there is a dislocation, the dislocation acts as a deep level, and we now have a competitive recombination event, and only some of the electron hole pairs that the electron beam generates will recombine to give a photon. And so we get much fewer photons close to a dislocation. And we can use this to our advantage to very rapidly screen semiconductor materials for extended defects, because in these materials, there'll be regions in an image or a map where the CL emission intensity is low. Now, one of the materials where this is most commonly employed is a material called gallium nitride. And gallium nitride is a compound semiconductor that's used widely in light-emitting diodes and high-power electronics. And it contains a lot of dislocations, and they are very bad for device performance in many different ways. But for quality assurance purposes, and to make sure that devices are going to exceed the design targets that we have for a device, it's important to be able to quantify the defect density. And we can do that using CL. So here is a schematic of a gallium nitride material, and it's grown on a substrate. That's partly important. It's important because where you have this substrate and semiconductor, at the interface, there is a mismatch, and that mismatch nucleates something called threading dislocations. So defects run from that interface between the substrate and the semiconductor up through to the surface. And they pretty much come to the surface at right angles, so they impinge as points on the top surface of our wafer. Now, using CL, we can image that top surface, and everywhere that there is an electrically active dislocation will show up as a dark spot in our CL image. So this CL map takes just a few tens of seconds to capture, and from it we're able to reveal all of the dislocations that are electrically active within our material and quantify them. So here, the blue arrows point to dislocations in our material, and when we count those black dots, we get to a dislocation density of about 5 times 10 to the 5 centimeter squared. Now that's an important parameter to know for people who are making devices based on this gallium nitride material. So not only can you use CL when you're at the material stage before you build devices, but you can also use it to monitor and watch the evolution of device failure. So here we have a laser stripe and 3 different lasers that have been turned on for some period of time and then analyzed when they show a failure, potentially likely, and particularly device B and device C have failed, and you can tell that from the current map over time. You see that it spikes rather dramatically, and the failure mode is can be seen from the CL data at the point when these line defects, these dark line defects, nucleate within the device. So you can use CL as a way of detecting and identifying where failure modes occur within your laser structures. So not only do we use CL for simple measurement of crystal defects and band gap in materials, there's a lot of things that you can tell, particularly about devices which are designed to emit light. So there's a range of materials called the nitride semiconductors, which a lot of light-emitting diodes and solid-state displays are manufactured from these sorts of materials. And CL is used widely to investigate these materials. And typically, historically, people have used CL to map the spatial variation in the emission of these devices. So this device that we're looking at here is actually some micropillars that have been fabricated by etching and then overgrowing different materials. And the bottom images on the left-hand side is a secondary electron image looking top-down on one of these devices. And on the right-hand side at the bottom is a cathodoluminescent spectrum image. So every pixel within this data set contains a CL spectrum. And so from this, we're able to determine the spatial variation in the emission spectrum. So at each of those points, we have a very different emission spectrum. The peaks change in their relative intensity, and actually some of them change form as well. They move around and they change shape. We can use this to extract distribution maps, revealing the spatial variation in the emission. When we overlay those, you see that we have regions of the specimen which emit very strongly preferentially at one wavelength compared to other wavelengths. So we have a very good understanding here of the spatial variation in the emission, and that's important if you're trying to grow these materials uniformly and optimize device efficiency. You can go a step further and do some mathematical analysis on this sort of data set. I'm not going to go into the details here. We may do a separate webinar on that at some point. But you can do from this things like calculate out the alloy composition, so the indium fraction of the material. And when you do this using a technique called nonlinear least squared fitting, you can see that you have indium clustering in certain preferential regions of the device. So this is very typically how cathodoluminescence has been used to analyze these sorts of light-emitting materials. On the next slide, I'm going to go into it very quickly, and the next slide is actually will be expanded in our next webinar. It's a slide which introduces probably a couple of new analysis modes which will be new to a vast majority of the audience listening. And so these new emission modes allow you to measure the emission pattern from devices, so the direction in which light is emitted. So here is that micro-LED ensemble that I showed you on the last slide. So it's a series of these micropillars. They're a few microns tall, and we're looking down on the top surface. And from that, we capture the emission pattern. using a technique or an analysis mode called angle resolved CL. So this data is a polar plot that describes the intensity, the emission intensity in a given direction. And what we see in this case is that we have a highly anisotropic emission pattern. So at around 50 degrees from the surface normal, we have this very intense bright ring showing that most light goes out at 50 degrees, whereas at the surface normal, so straight back at us as we're looking down, in the center of this plot, we have very weak emission. Now, that's a little unusual for people who've been doing CL for a long time, especially if they've been looking at thin film type devices. But when we relate this back to the sample structure, it becomes more obvious why. So the sample is in cross-section, has this type of schematic diagram, and the facets that you see here and here are inclined to the surface normal at about 50 degrees. So the light preferentially comes out at those facets, and very little light is emitted straight back up towards the direction which the electrons came. So we can directly relate the shape and structure of these devices that we've fabricated to their emission pattern. And we can do that over an array of LED pixels or micro LED pixels that we've done here, or individual ones. So we can correlate the structure, the spacing to the emission pattern and get a very good understanding of the display. However, one very important parameter for people making displays based on these is everybody's color experience the same? This data that I've shown you so far is simply an intensity emission pattern. To really understand whether you have uniform emission, not only in intensity, but also in color, you really need to have spectroscopic analysis of the emission pattern. And for that, brand new, announced within the last few months, is a technique that we've developed called wavelength and angle resolved CL. What I'm going to show you is a short video that shows you the emission pattern at throughout as I change the wavelength of emission. And the emission pattern is being color coded according to its wavelength, according to the scale that you see on the bottom of the screen. So I'm going to start the video, and you'll see that we start off in the ultraviolet, which is why it looks outside of the visible at the moment. And as we go through the visible region, you'll see that the emission pattern dramatically changes as we vary the emission wavelength. So what this tells us is that we have very highly anisotropic emission color from these devices. And if you're trying to fabricate a display from a display or a light emitting diode from this sort of material, then it's important that you have a way of characterizing it and relating it directly back to the structure, because the structure is critical to the way in which the intensity pattern or the emission pattern, both in terms of its intensity and its color. So the next webinar will have a lot more detail on how we perform this analysis, and that'll be, I'll tell you when that is at the end of this presentation. So before I end the presentation, I'm going to go on to the last sort of set of application topics that I'd like to discuss, and that's a topic called nanophotonics. And this is really photonics, optical properties of materials below the diffraction limit. So really understanding light and matter at the nanoscale. And it's interesting, partly from a fundamental perspective, because it has lots of interesting physics that takes place, but also because there are a lot of novel optical designs that are made possible by this plasmonic metal-based nanoparticles. And really, you can get really surprising enhancement in light emission and absorption, and you can control that by changing a sample size, shape, and composition. And it's all to do with the way that the light causes resonances of the free electrons within the metal, and it leads to greatly enhanced electromagnetic fields. Now, what's important for researchers is to be able to reveal this plasmon resonance modes within a material and the emission properties of the light in terms of its polarization and direction. However, it's a really challenging thing to do experimentally, particularly in optical techniques, because these nanoparticles are below the diffraction limit of light. Fortunately for me, energetic electrons, like we have in a scanning electron microscope or a transmission electron microscope, can be used to generate surface plasmons and then study the surface plasmon behavior at a spatial resolution that we need to. So if you were concentrating at the start of the presentation, you should recognize this image on the left-hand side. So this is my image that I used to demonstrate spatial resolution of various different luminescence techniques at the start of the webinar. And in the center, so these are gold palladium nanostars, and they've just been drop cast from some solution onto a non-luminescent substrate and then plasma cleaned to remove any organic residue. In the center is an individual gold palladium nanostar, and these are about 80 to 100 nanometers tip to tip. So very small, below the diffraction limit of light. So something that you would not be able to see individual nanoparticles in an optical setup. In cathodoluminescence, we can excite them and measure the emission. And here we have polarization filtered CL spectrum images captured in just 2 minutes. So these nanostars enhance the light emission at a wavelength of about 600 nanometers, because each of these pixels contains a wavelength spectrum. And the local density of optical state maxima occur at the resonance node, so at the nanostar tips. And the spatial resolution here that you see is better than 20 nanometers. So these resonance nodes at the tips are separated by 20 nanometers, and our resolution is clearly better than that. Now, we use in this map 2 different polarization filters to separate out different linear polarizations. And what you see is that 2 tips opposite or orthogonal to each other, or the 2 tips opposite each other emit light with the same polarization, and the ones orthogonal emit at a polarization rotated by 90 degrees. And this differing emission polarization suggests that the most intense plasmonic modes are dipolar and resonant at opposing tips. So this reveals deeply the physics that are going on within our material. So not only can we collect the emission spectrum and reveal the local density of optical states and the polarization, but we can also determine the emission direction of the light that's emitted from these particles. So really reveal how light and matter interact at the nanoscale. And the angle resolved CL pattern that you see on the right-hand side reveals that the emission pattern to the direction in which light is emitted is orthogonal to the respective dipole axes. You can see that the blue dipole is in this direction in the spatial map, and then it's orthogonal in the angle resolved plot. So this is a very powerful technique which gives us a very detailed understanding of how light and matter interact really far below the diffraction limit. So down with tens of nanometer spatial resolution. So that's the end of the application focus slides that I wanted to go through with you today. I'll just summarize before going on to answering a few questions that came in during the presentation. So hopefully all of these you should have remembered from the presentation, but cathodoluminescence microscopy is a luminescence spectroscopy which offers potentially nanometer scale spatial resolution. And just as importantly, and in some cases more importantly, it enables the correlation of the optical and electronic properties with the sample structure, composition, crystallography, morphology. We use this information in a variety of ways, including revealing the geological history through trace element chemistry, so performing geochronology studies, thermobarometry, revealing different generations of crystallization. We can reveal the electronic structure of semiconductor materials and devices and their defects, quantify the defects within them and their distribution, and also now reveal the isotropy of color rendering in display applications. We can also characterize in nanophotonic materials how light and matter interact at the nanoscale with spatial wavelength polarization and directional resolutions. Okay, so at that point, I'm going to remind you all that you can submit questions. All questions should be submitted through the questions page, or the questions pane, which appears on the GoToWebinar bar on the right-hand side of your screen. Any that I don't get through now, we only have a few minutes left, we will answer, and I will answer within the next week. So any outstanding questions will be addressed offline, and the webinar recording will be available for 5 days. There will be a recording posted to the Gatan website, and a download link will be provided to all registrants by email. And importantly, within that email, please make sure to take a look at the possible topics for this Cathodoluminescence Explained webinar series to address in future. And within that document, or within the email, there will also be the possibility of suggesting your own. And if there is enough people who would like to see a particular application or operational method addressed, then we can do that in a future webinar. And just to say, the next webinar an invite will come out to you all, but it is being scheduled for the 15th of May. Okay, so just let me answer a couple of questions before we finish up. So the first question that came in is any special sample preparation needed? Well, in most cases, no, and that's particularly the case for if you're doing CL microscopy in an SEM. There are some times when you might need to think a little bit in terms of the substrate or the epoxy that you use to mount your specimens, as you preferably would like a non-luminescent background for the analysis or the analyses that you'd like to take. So there's a small amount, but mostly, particularly with semiconductor materials, you can put a wafer directly in and start analyzing almost straight away. The next question is, how long does data collection take? Well, the answer there does depend slightly on the type of analysis that you want to perform. As a generalized statement, I'd probably say that some of the unfiltered maps, if you wanted to count dislocations, those sorts of maps can be collected in just a few seconds, a few tens of seconds. Some of the more detailed analysis where you have full spectral and polarization characterization may take several tens of minutes. Okay, and I've got time for one last question, I think, before we finish up. And okay, here we go. So last question, is cryogenic cooling required? Well, the answer to that is a little bit complicated, and it's probably something that we'll address in a future webinar in more detail. But for most materials, or nearly all materials, it's not necessary to cool the sample to get some light out of them. But whether that light is interesting for you may depend on the temperature in which you run the analysis. So there are some particular use cases. For example, if you want to be able to not only reveal the presence of extended defects within a semiconductor, but you actually want to be able to study their electronic structure based on their luminescence signature, then actually cooling the specimen down to nitrogen in some cases, or helium temperatures, many of those defects then become luminescent themselves. And the spectrum that you capture from that material then gives you information not only about the perfect crystal, but also about the electronic structure of the crystal defect as well. So I hope that is a short answer to what is potentially a complicated question. Okay, so then I'm going to say thank you for your time and attention and listening to the webinar today. And we hope to see you at the next webinar, the 15th of May. And a reminder that if you would like specific subjects to be covered by this series of webinars, then please complete the feedback in the email that comes around after this webinar, and feel free to suggest your own topics. And if there is critical mass, then we will address that as well. Okay, so all questions that haven't been answered, I will address within the next week. So thank you all for your time today.